Welcome to this explainer. Today, we're going on a fascinating evolutionary quest. Whether you're typing a prompt into ChatGPT, asking your phone for the weather, or relying on autocomplete to finish that email, we're going to figure out exactly how we take something as messy, complex, and, well, beautiful as human language, and teach it to a machine that is fundamentally made of math. So, let's dive into this. How do you teach a machine made of numbers to actually understand human words? That exact question represents the central conflict of natural language processing, or NLP for short. See, we humans communicate in concepts and nuances, right? But computers, they literally only understand zeros and ones. Bridging that gap is absolutely one of the most exciting challenges in modern tech. To see how we got there, we'll follow this ladder of understanding today. We'll start with how computers read text, move into counting with bag of words, mapping meaning with word vectors, look at the essential NLP toolkit, and finally end with the context revolution, transformers. We're climbing all the way from basic counting mechanisms to state-of-the-art, context-aware AI. Let's jump right into Section 1, How Computers Read Text. We've got to start with the absolute baseline of how we even prepare a sentence for a computer to digest. And here's the core rule you have to remember. To a data model, a word is completely meaningless unless we can successfully convert it into a numerical representation. If you feed a computer the word book, it just sees a random string of characters. We have to translate that text into a mathematical vector it can actually calculate. No math, no understanding. Let's see how this builds with our very first major modeling technique in Section 2, counting with bag of words. The absolute simplest approach to that translation problem works like this. We basically construct a dictionary of every unique word we've ever seen across all our data. Then, for any new sentence, we just assign a 1 if the word is present and a 0 if it isn't. It's essentially a giant, rigid binary checklist. So, a heartfelt phrase like, "I love the book," just gets coldly mapped out into a vector of ones and zeros. But, here's the fatal, rigid flaw of bag of words. Say we train our model on the word book and successfully teach it to categorize phrases into a books category. If we then ask it to categorize "I love the story," it fails miserably. It might guess it belongs in clothing, which makes no sense. Why? Because it has literally never seen the exact word story before. It doesn't know what story actually means. It just knows that the word book is missing from its checklist. To fix this huge blind spot, we step up to the next major innovation in Section 3, mapping meaning with word vectors, utilizing powerful libraries like Spacie. Now, here's how we solve that vocabulary problem. Word vectors convert text into numerical vectors that actually capture semantic meaning. Instead of a simple binary checklist, these models learn meaning by analyzing the context windows surrounding tokens. This naturally clusters related words together in a multi-dimensional mathematical space. It's really cool. By feeding hundreds of thousands of sentences through these neural networks, the computer just automatically learns relationships. It figures out that red, blue, and yellow map together. It learns that story and characters link together. It learns that read and book share spatial proximity. Suddenly, the machine understands that book and story actually belong in the exact same conceptual space. Game changer, right? Well, hold on, because standard word vectors suffer from their own critical blind spot, words with multiple meanings. If you average the word check into a single static vector, the computer completely destroys the nuance. It hopelessly blends a financial bank document together with the act of verifying a checkbox into a single confusing number. Before we solve that tricky context problem, let's take a quick interlude into Section 4, the essential NLP toolkit. This is the Python code we use to prepare and clean text before it ever hits those big models. First up is regex, short for regular expressions. This is powerful pattern matching used to find specific string structures. Regex is absolutely vital when we need complete precision, like making sure a word search for the standalone word read doesn't falsely trigger just because it found those same 4 letters hiding inside the word tread. Next, we've got to normalize our data. We use stemming to algorithmically chop off word endings, cutting reading and books down to read and book. But sometimes that actually creates non-words. So we also use lemmatization, which utilizes a dictionary to intelligently reduce words back down to their true canonical roots, cleanly turning stories into story. Then we have stop words. Using tools like NLTK, we just ruthlessly strip out highly common English filler words like the, it, or is. Basically, we're tossing out the grammar that doesn't add any core semantic meaning to the sentence. This prevents our vector averages from getting all bogged down. And utilizing a library like TextBlob brings it all together to do rapid-fire data cleaning. You can trigger instant spell correction, automatic part-of-speech tagging to separate nouns from verbs, or even assess a review's positive or negative polarity with sentiment analysis. And incredibly, you can do all of this with literally a single line of code. Okay, let's jump back to our context problem. Remember where the word check was getting all confused? Let's step up to section 5, the context revolution, transformers. This is the ultimate triumph of modern NLP. To really understand the revolution, we have to look at what came before it. Older architectures like sequential, recurrent neural networks read sentences strictly sequentially, moving one word at a time. This meant that in a long sentence, they often suffered from short-term memory, literally forgetting a crucial early word like bank by the time they finally reached the word closed much later in the phrase. Then came a famous paper called Attention is All You Need. And honestly, it changed the world. It introduced attention, a breakthrough mechanism allowing models to look at an entire sentence at once. The neural network essentially asks relational questions about the whole phrase in one go, calculating how relevant every single word is to every other word simultaneously. That led directly to transformers and models like BERT. Models like BERT take this to the next level by being bidirectional, meaning they read context simultaneously from both left to right and right to left. And brilliantly, these massively powerful networks were open sourced, so anyone could just download and fine-tune them. Because of this attention mechanism, BERT flawlessly untangles the nuance. It reads, "I need to write a check," and perfectly classifies it as banking. It reads, "Check out this book," and perfectly classifies it as books. It completely fixes the final frustrating blind spot we discovered earlier. We've climbed all the way from rigidly counting ones and zeros to machines that deeply and fluidly understand human nuance. And this journey leaves us with a fascinating final thought for this explainer. As models like BERT and GPT continue to learn and master our context, what will computers ultimately teach us about our own language?